All right, welcome listeners to the first lecture of Chemistry 220b, the Advanced Graduate Statistical Mechanics course. What I like to refer to as the statistical mechanics of fields, fluctuations, and phases. This is an advanced course. It is differentiated from introductory courses in a couple of important ways. So those of you who have taken an introductory StatMech course with me know that the primary objective of such a class is really to introduce you into a way of thinking about how macroscopic properties arise from microscopic fluctuations, correlations, and behaviors. That really is the primary objective of statistical mechanics generally, is to build that bridge between the macroscopic and microscopic world. Now, in an introductory class, you're given enough time essentially to become familiar with the basic assumptions, why it should be a reasonable thing to try to do to build that bridge. And depending on the specifics of the course, you might get into some concrete examples, illustrate some simple properties of matter that arise from its underlying microscopic constituents. Largely, the focus on introductory courses will be in simple non-interacting systems like ideal gases and maybe very simple solids, which can feel very removed from the sorts of systems and materials and processes that you might be actually interested in your day-to-day life or in your research. The simplicity of thinking about such systems admits exact calculations and thus an expansion on the kind of underlying foundational principles of StatMech. But the drawback is that it's really hard to translate those exact calculations to the messy systems that you might be interested in, things like liquids or macroscopic assemblies of proteins, solids that aren't described by simple harmonic motion. Even gases that are somewhat dense are not well described by ideal or non-interacting models. And so if introductory courses are the statistical mechanics in principle, this advanced course really aims to be statistical mechanics in practice. We will trade in idealized systems for messy ones at the cost of doing very few exact calculations and rather focusing on how one approximates calculations in interacting systems and thus make some progress towards understanding their behaviors and macroscopic consequences. So really, largely this class will develop a set of approximate theories, models, and approaches, but with a real aim to provide you the tools to then apply those approximate techniques in your everyday life and research. So a quick note. So I am going to be your instructor for the year. My name is David Limmer. Together with my student, Yoon Jae Park, who will be your GSI. We hope we can convey as much of this knowledge as possible, given the constraints that we'll be doing all of this virtually. And before I get into the first lecture, which will largely just be some review of the basics of StatMech, which will provide kind of a common language and set of notation with which we can then proceed, I want to flesh out a little bit of the sorts of things that we aim to cover in this class a little more concretely. So to do that, let me give you some examples. So a primary objective in the first part of this course is to learn how to predict the properties of liquids. So a canonical liquid shown over here on the left is something like water. A property of water we might want to predict is its structure, its local environment. Water is a phase of matter where interactions are of paramount importance. A gas would not condense if it did not attract its constituent pieces. And yet, the fact that it is disordered, that there's no long-range repeating units, makes standard theories applicable in the solid state not tenable. And so we'll develop a theory of liquid structure. And I think importantly, a real aim of this class is to be able to make direct contact between such theories and actual measurements. So for example, how do we know what the structure of a fluid is? That's by doing scattering experiments, like I've kind of illustrated over here on the right. An X-ray scattering experiment produces something known as the structure factor, a modulation of some intensity in wave vector space, given some X-ray scattering experiment, which can be inverted and give us information about how molecules are distributed relative to each other. So not only will we develop a theory for the liquid structure, but we'll develop a theory for how scattering works and how it encodes liquid structure. Analogously, we will think about not just scattering in K-space, but in frequency space, and specifically how light intensity is modulated and absorbed when it's shined on a liquid, which gives us information about not just its statics, but its dynamics. So theories of line shapes for linear absorption, for example, considering maybe the OH vibrational relaxation of a water molecule, like illustrated here over on the right. That will be an aim of this class as well. We won't think about just pure fluids, but also fluids that contain things, solutes, for example. A canonical example of a typical solution you might want to describe would be an ionic solution, like I've shown here, or I've embedded some sodium and chloride. We'll develop early on, actually one of the first things we'll do in just a couple lectures is the theory for how ions distribute themselves in a solution, in a polar solution. But more than just statics, more than just equilibrium statistical mechanics, we'll think quite hard about the dynamics that evolve within that state, both rare dynamics like how ions dissociate through the fluctuation which takes it over some very improbable set of states. This is encoded in transition state theory and the estimation of rates of rare events, but also linear transport properties, things like how a solution with free charges conducts if I apply an electric field. We won't confine our attention only to liquids, but also to the solid states. We'll think a little bit about solvation in solids, most notably in the context of how electrons interact with their surroundings, say in a semiconductor, working through what's called the polaron problem. Like I've kind of shown as a cartoon here, this purple blob is an isodensity surface for an electron charge density surrounding or embedded in a solid. The localization of that electron is precisely due to its strong interactions with its environment. Again, contrasting just a static perspective, we will also think about how electrons dephase or scatter through those materials. Near the end of the class, we will think about more exotic states of matter and construct general theories to describe the transitions between those states of matter, like illustrated here. When you take a block copolymer, its phase diagram can be very complex, much more complex than just a liquid vapor transition like we built the tools to described in the introductory course. We will, in between, developing really nonlinear theories for matter, like is required in the topic of phase transitions, also consider systems that are driven far away from equilibrium. And I hope to get to a discussion of a very contemporary set of questions concerning so-called active matter, like I show here. These are models for things like bacteria that swim around in solution, or light-driven colloidal materials that, even though they are not attractive, can phase separate, like shown in the movie, due to the fact that they continually dissipate energy. They consume energy, transfer it into directed motion, and result in non-trivial pattern formation, like the aggregation behavior illustrated. So that gives you kind of an overview. Though all of these sorts of things, you will be in a position to describe, predict, and explain with the tools that we'll develop. A few notes on practicality. So again, as I've said, I'm the instructor, David Limmer. Here's the course syllabus hosted on B courses. I will largely communicate with you all through B courses. I will upload lecture notes and these videos to the site. We will announce practical matters in it as well. Yoon Jae Park will be coordinating this with me. A note about the format. So, due to COVID restrictions, we aren't meeting in person, obviously. So what I aim to do in this class is to record lectures like I'm doing today, post them in advance of the week. So I will record 2 lectures and post them the weekends before our week of study. And then I hope to have small group live sessions where I can meet with you all and discuss the content of the lectures. I will, on Tuesday's live session, which will be, the first week will be a little bit distinct in this regard, I will hope to sort you into those small groups and establish what are good times to meet through the week. In addition to small group discussions and these posted videos, Yoon will also hold office hours, more kind of traditional office hours done through Zoom, with a link that will be hosted in the syllabus. And additionally, she'll host bi-weekly discussion sections, which will largely serve as a time to go over some of the more complicated math that is required for this course, things that you likely have not had lots of exposure to before, things like functional analysis, functional calculus, Laplace transforms, which some of you might be familiar with, and some specifics on probability theory. You can read, as you like, the synopsis of the course. We don't have a specific textbook. I've listed a number here which are relevant for different parts of the class. I will largely follow the LaTeX course notes that I will post along with these lectures. I'll largely post those in batches ahead of time. And then one final note about how the course will actually be graded. So largely your grade will be determined by a set of problem sets posted through the year. There will probably be about 7 or 8 of them. They are difficult, and you'll have about 2 weeks to do them. I am perfectly happy with you all working in groups, though you should be turning in your own assignments. So at the end of the day, I do not want to see 2 people uploading the exact same PDF. You should have something distinct to show for your own work relative to your neighbors. That will take up about 2/3 of your grade. The remaining third is a project that you will work on through the course of the semester, beginning in about a month, which is really what I hope imparts the utility of this class for you all. So this project aims to have you actually delve into in a little more depth, and we will cover some aspect of the class, some theory we've developed or some method or idea we've presented, and actually apply it to your own work. This will be done in close concert with me and through discussions. And at the end of the semester, you'll write a report to kind of show what you've learned and how it gave you some new insight into the sorts of problems you're interested in. The specifics about this project and the report and the requirements for it will be posted later on in the semester. Apart from that, the syllabus shows a rough outline of the sorts of things we'll study. And I think that's about it for that. Okay, so those are the practicalities. Today, before we really get into kind of new material, I want to just take the lecture to remind you of some basics of statistical mechanics, some basic manipulations that we learned in introductory courses, connections between microscopics and thermodynamic properties. And we'll start sketching out in this discussion a kind of change of philosophy that we'll adopt in this course. Because again, our emphasis really is on approximate techniques to solve messy systems. We need to think a little bit differently about how we approach the application of statistical mechanics to such cases. We aren't going to aim to write down a Hamiltonian and compute the partition function, because such things will not really be practical for the sorts of systems we're interested in. So we need to figure out how to ask different questions. And so that the beginnings of some intuition for that will be illustrated near the end of this lecture. Okay, well, let's go ahead and start with some background. Okay, so one of the first things you learn in statistical mechanics is that we know for a system at thermodynamic equilibrium how microstates of a system, all of the gory details that describe dynamically the state of the system, how they are distributed. And a system with fixed number of particles, volume, and temperature, the probability of seeing a microstate is given by a Boltzmann distribution, or an exponentially suppressed probability with the energy of that microstate weighted by this factor beta, which encodes the temperature of the surroundings, and normalized by what we call the partition function Q. And largely, the aim of introductory courses is to compute this Q, noting that it is given explicitly as a sum over these Boltzmann factors. One aims to do that because that partition function has a thermodynamic meaning. Specifically, if I take its log, multiply by kBt and a minus, that is exactly equal to, in this fixed NVT ensemble, the Helmholtz free energy. So this is one of the first bridges one builds between the microscopic and macroscopic world. Of course, the macroscopic world is determined by thermodynamics, at least in equilibrium. Spontaneous processes correspond to specific changes of free energies. And here we have an explicit way of computing free energy through the evaluation of a partition function. And a lot of the introductory course is spent then trying to compute this, understand these relationships, and to do so really largely limits the sorts of systems that one can study. For example, for systems that are identical and made up of independent particles, such that the energy of some microstate can be written as the energy of particle 1 plus particle 2 plus particle 3. The partition function is something that's easily evaluatable because it factorizes. So Q can be written as the microstate sum over particle 1, sum over the microstates of particle 2, particle 3, etc. This Boltzmann factor and the sum of the energies of those states, of those individual single particle states. If the particles are identical and indistinguishable, we have a factor of n factorial associated with the permutation symmetry of these indices. And you learn that the linearity of the argument of that exponential allows one to manipulate this expression for the partition function into a product of n terms which are all the same and correspond to the evaluation of just a single particle partition function. Denoted here as little q. And indeed, if the single particle is somewhat simple, like it only translates or rotates, that little q can be evaluated. For concreteness, one could consider just free particle motion such that the energy of that individual particle is just its kinetic energy. And for the whole system, thus, is just a sum over the individual particles' kinetic energies. M here being the mass of the particle, P being its momentum. The microstate of one of those particles is just given by where it can be and how fast it's going. R is in some container V. P can take any value from minus to plus infinity. And that sum, often naturally expressed as an integral, can be evaluated explicitly, giving rise to, in a few steps, things like the ideal gas law. And it's really small deviations away from those sorts of calculations that one does in an introductory course, and we won't reprise here. One of the few interacting systems is amenable to explicit exact calculation. Which is often done in an introductory course. And that's a set of harmonic oscillators. It's worthwhile to work through this, an example of a system of harmonic oscillators, in a little detail to remind you how this will work, because this is it encodes a couple tricks that we'll use a couple times or many times in this course. So the Hamiltonian, or the energy function for a set of harmonic oscillators, includes both a potential and a kinetic term. The kinetic term is, as it is in the free particle case, the sum of individual kinetic energies of the n particles. Indeed, in a classical limit, each of those can be evaluated independently, giving rise to Maxwell-Boltzmann statistics for particles' speeds. The potential of a set of interacting harmonic oscillators will have some constant ground states plus a double sum of deviations of each particle relative to their equilibrium positions, weighted by some spring constant. So let's let Ri naught be the average position of particle I, and Kij be a matrix of spring constants. As written, that potential energy function depends instantaneously on both what particle I and what particle J is doing in a way that's not separable. I can't write out in a simple way the energy of just particle I without knowing the dynamical state of particle J. So this is indeed an interacting system. However, harmonic oscillators are simple in that by diagonalizing that matrix of spring constants, K, we can find a set of normal modes call them C, which subsequently uncouple the oscillators. Allowing us to write the Hamiltonian in terms of those normal modes. If I start with n particles, I'll have n normal modes with the momentum of that mode and a corresponding potential energy of that mode. Now that is a Hamiltonian, which is now expressly separable. Each I mode now fluctuates completely independently. So we start with an interacting system, but by viewing it in a specific representation, in this case, a representation of normal modes, we have a free system, a system which is non-interacting. So this sort of manipulation you'll show explicitly in your first homework set. And one of the first goals of this class will be to figure out analogous sorts of tricks to study interacting systems like liquids, where the meaning of normal modes is not as transparent. I think you're taught at an early age how to think about normal modes of solids or of small molecules, thinking for something like water as symmetric and asymmetric stretches. What would it mean to try to discover the normal modes, the harmonic motions of a liquid? Liquids are diffusive. They don't undergo small displacements around some equilibrium position. So looking at just the bare positions and trying to write harmonic degrees of freedom for those bare positions is not going to work. Nevertheless, we will show in a couple lectures that there are collective coordinates, turns out to be the density, which do, to a very good approximation, behave in a harmonic way, allowing us to use the same trick we've just illustrated here to describe liquids. Once we have a set of uncoupled oscillators, we can evaluate essentially everything we would want for them. And so let's go ahead and do that, because it will give us the opportunity to remind ourselves of another important fact for classical statistical mechanics, namely the separability of configurational and momentum degrees of freedom. So for a single harmonic oscillator, which could be one of those ith modes, we have a Hamiltonian, which is a potential and a kinetic piece. Let's consider this in as simple a way as possible in 1D. Let's write out the potential as x squared over 2 alpha, alpha then being something like the inverse spring constant for this single harmonic oscillator. And let's write down the kinetic energy with momentum. So again, x is going to be some displacement of the particle from its equilibrium position. From Boltzmann's statistics, we know immediately the probability of seeing the particle at position x and moving with momentum p, which is going to be given by the Boltzmann factor of its energy, e to the minus beta u of x minus beta k of p. up to some normalization constant. And now for a classical system, U and K are numbers, not operators, which means that I can separate that exponential. The exponential of a sum is the product of exponentials. Which implies that the statistics of X and the statistics of P are completely uncorrelated. They factorize. For classical variables, this is of course true. And quantum mechanically, it is a good approximation up to order e to the h bar. So one often thinks about classical mechanics as the limit where h bar is equal to 0. The fact that the kinetic energy is where the mass of the system lies, where the information of the mass lies, tells you immediately that things like isotope effects for thermodynamic properties are intrinsically quantum mechanical. Now this is a proportionality. We can go ahead and, in this instance, compute the normalization constant. For this single harmonic oscillator, the partition function is given by an integral over x times an integral over p, weighted by these Boltzmann factors. And now, because x and p are continuous variables, we have a little bit of an awkwardness here. If I just left the expression as is, I would have endowed the partition function with units. It is a sum of exponentials and therefore unitless in its original definition. So I really need to count these states with some resolution. Call that resolution delta x times delta p. That's an awkwardness that is inherited from classical mechanics. Because in principle, there is an infinite number of states along the x direction and an infinite number of states along the p direction. But saying that the partition function is infinity is not a useful statement. So we decide to, by fiat, introduce a resolution. Now, because I can separate those exponential factors, I can associate the integral over x with the factor associated with its potential energy, and separately the integral over p with its kinetic energy. That integral, of course, is a Gaussian integral in momentum, which can be evaluated. When I evaluate it, however, you will note, if I define this, let's do that in red, this term here as Q config, that's where all of the X dependence lives, all of these spatial states are located. That Q config as defined has units of X. So it must be that when I evaluate when I integrate the momentum degrees of freedom, I will end up with a new effective resolution to count those spatial states in. So one often thinks about the effect of momentum fluctuations as renormalizing the effective spatial resolution for counting spatial states. To evaluate that integral, which is a Gaussian form, we have to remember how to do Gaussian integrals. They have a form like so. For some variable y, a form of a Gaussian integral would be something like this, which can be evaluated by one way is by squaring it, doing the integrals in polar coordinates and then taking the square root. Alternatively, one can use Feynman's trick of differentiating under the integral. Both will give you the result that Gaussian integrals are equal to the square root of 2 pi times sigma squared, where sigma is in the denominator of the argument of the exponential. This is such an important result, I will box it. That integral we will use quite often in this class. Doing that integral for momentum, we would recognize that sigma squared is being played by m over beta, which would give us an expression for lambda. If we, in addition, note that quantum mechanically, a reasonable choice of resolution would be that delta x times delta p is Planck's constant. That gives us a way of counting states that turns out to be a reasonable way to do things. We would arrive at a definition for this so-called thermal wavelength, which is Planck's constant over 2 pi m over beta square root of. That's the thermal wavelength of a particle with a mass m and a temperature T. So we go through this example of a harmonic oscillator, both to remind you of the separability of momentum and position, as well as to remind you of when such an approximation is good. That thermal wavelength essentially gives us a length scale for denoting that when a classical approximation is reasonable. A classical approximation to a system of interacting particles or non-interacting particles when that lambda is much, much smaller than some characteristic size of the particles. The thermal wavelength essentially encodes how delocalized a point particle is quantum mechanically due to quantum mechanical uncertainty. And so if that length scale is very small, the particle is well localized, we can essentially treat it as a point particle with no spatial delocalization. So from that factorization, we know that we should find that the probability of seeing the particle at some x state is independent of p. One way to write that down would be explicitly to take the joint probability of x and p and integrate over all p. We can express that joint probability as the Boltzmann factors for position and momentum divided by their respective partition functions, which we've just explicitly evaluated for momentum. Noting that all of the position dependence in the numerator is in that exponential, which can be pulled out from the top. Again, this one can be passed through that integral there. We're left with a ratio of these integrals over momentum, which are identical and thus cancel. And so indeed, the probability of seeing the position of the particle x is just encoded by its potential energy and its configurational partition function. So from the marginalization over the joint probability, we can find that indeed, classically speaking, all of the statistics of spatial arrangements, all of the information about how particles distribute themselves in space is encoded just in the potential energy and its corresponding partition function, without knowing anything we care about, without needing to know anything about momentum or its fluctuations. And using, again, our Gaussian integral, if we actually were to evaluate this configurational partition function, which we can do, we would find that it is the square root of 2 pi alpha over beta. And thus we have a explicit expression for the probability distribution of seeing a particle at some position x, which is independent of its momentum. And is Gaussian distributed in the case of this harmonic oscillator. If we were to plot that, In this case, X has a maximum at 0. It's most likely to be at its equilibrium position. Exponentially decays with initial quadratic curvature, and a Gaussian distribution has some finite width, which in this case is given by the square root of that inverse spring constant divided by beta. Knowing the Gaussian distribution is defined by a mean and a variance, we can pick off what the variance of this Gaussian random variable x is as just alpha over beta, square root of that thus being the standard deviation, giving us the width of that distribution. Once we have the distribution and the partition function, all of thermodynamics follows. For example, the free energy due to those configurational degrees of freedom minus kBt log of the configurational part of the partition function is this minus kBt log. The partition function was the square root of 2 pi alpha over beta. I could raise 2 pi alpha over beta to the 1/2, and then the log of that I can pull the 1/2 out, which gives me minus kBt over 2 log of 2 pi alpha over beta. So that's the free energy of a harmonic oscillator. The average potential energy of course can be computed by taking the derivative of log of the partition function with respect to minus beta. Let's go ahead and explicitly call that the potential energy. And in this case, the potential energy on average is given by 1/2 kBt, which you all will remember is a reflection of the so-called equipartition theorem. We can keep going if we have the Helmholtz free energy and the potential energy due to those configurational degrees of freedom. The entropy can follow suit. As usual, we'll denote entropy as S. It would follow from the identification that the Helmholtz free energy is defined as the energy less T times the entropy, or that the entropy is equal to the average energy less the Helmholtz free energy divided by T. In this case, the entropy of our single harmonic oscillator is 1/2 kB plus 1/2 kb log of 2 pi alpha over beta. Just as a bit of a reminder of how one can decompose free energies into energetic and entropic contributions. This also serves as an interesting way of seeing where classical mechanics breaks down. If we took the limit that t goes to 0, the log of 0 is of course minus infinity, but it doesn't make sense for the entropy to diverge to minus infinity. That inconsistency, of course, is a reflection of the breakdown of our classical approximation. When we go to really low energies, a harmonic oscillator, or really low temperatures, a harmonic oscillator would not, or would get stuck in some low ground state with 0 point energy. There would be at least one state for it to occupy. The entropy due to Boltzmann is the log of the number of states. If there's one state, the log of 1 is 0, not minus infinity, which this classical calculation is suggesting. Okay. So this is an exactly computable model, the harmonic oscillator, which has just illustrated, or just been useful to us to remind ourselves of a few facts. For classical systems, configurational and kinetic degrees of freedom are separable. So it will suffice if we are only interested in configurational or structural degrees of freedom that we can consider those separately. We don't have to worry about what the kinetic energy or momentum degrees of freedom might be doing. Away from classical limits, of course, this will not be the case, and we'll have to think of alternative ways of incorporating quantum mechanics into our descriptions. But a lot of what we'll do early on will be to work explicitly with just configurational degrees of freedom, ignoring the fact that there is in fact conjugate momentum whose statistics are trivial. It also let us remind ourselves about some thermodynamic relationships, how we actually manipulate partition functions to get averages, how we relate partition functions to free energies and decompose those into energetic and entropic contributions. Okay, with that being said, most of what we'll do in this course is not to try to evaluate explicitly the partition function, because doing so will be too complicated. Rather, we will set our sights on a slightly different sort of question, which is not what is the partition function for a full system, or what is the free energy of a system. Rather, we will imagine that what we actually care about is how a system responds to some change. You can think about this as a perturbation theory. We're going to imagine that there are reference systems that we can understand or compute. And rather than trying to put ourselves in the difficult position of evaluating specific information of those reference systems, rather we'll imagine we can evaluate those and then try to work out expressions and relationships for how they respond to perturbations. And so let's do this first to gain some intuition in the context of our harmonic oscillator, in this case under a constant force. Okay. So a constant applied force can be applied to a harmonic oscillator by introducing a linear potential to that harmonic oscillator. So if initially we had a harmonic potential in which deviations of x from its equilibrium position resulted in an increase in its potential whose rise depended on the value of its inverse spring constant alpha, we can apply a constant force by subtracting from that potential minus F, the magnitude of that force, times x. This is, of course, a constant force because the force on a particle is minus the gradient of its potential in one dimension, just the derivative of its potential, minus sign. That is minus x over alpha, the restoring force due to the harmonic potential, plus the constant force, little f. Now let's ask, what happens to our initial harmonic oscillator when we add this force? Let's go ahead and work within the partition function language. Let Q of F be the partition function of the system in the presence of the force. And we can write that partition function. Again, we will essentially proceed throughout now, ignoring momentum, unless otherwise stated, because we're explicitly thinking about quantum mechanical degrees of freedom. We will also ignore the fact that we count states with some resolution, because the momentum is what's endowing the system with some effective resolution. And so we will only be concerned with what we previously called the configurational partition function, which has units of space. I will just drop the subscript config throughout the remainder of the course. Unless otherwise noted, it is meant to be just the integral over the spatial degrees of freedom weighted by its spatial potential. In this case, x squared over 2 alpha plus beta fx. And let's imagine that the domain of that integral is plus or minus infinity. Now, if we stare at that, we notice that the argument of the exponential has those two terms due to both the linear applied potential or constant force and the original harmonic potential. Again, as a sum in an exponential, I could factorize that exponential. Like so. Multiplying by 1, in this case, a partition function in the absence of the potential, of the added force, excuse me, and noting that that partition function sitting in the denominator of this Boltzmann factor under the integral is the averaging operation, we find that we can write the partition function of a harmonic oscillator under an applied force as a product of the partition function in the absence of the force times an expectation value of e to the beta f times x averaged in the absence of the force. So that expectation value, again, is the highlighted averaging operation. It tells us that there are simple relationships between the statistics of the system in the presence and absence of the force. By knowing about fluctuations in the absence of the force, I can predict what happens to the system in the presence of the force. That's the left and right hand sides of that equality. That expectation value, it's a average over a Gaussian distribution, the highlighted probability distribution, and can be evaluated explicitly, yielding an expression for Q of F, the partition function in the presence of the force, as it in its absence times a factor of e to the beta alpha f squared by 2. This is a consequence of another Gaussian integral. One worth committing to memory if I have the integral I as an integral over all space, some fluctuating variable y with measure minus y squared over 2 sigma squared, and I am averaging a linear function of y, in this case with some coefficient a, in this distribution is normalized. I can complete the square in the argument of the exponential, and thus have a new Gaussian integral with a shifted mean, allowing me to evaluate that integral in a simple way, always leading to this answer. So that's an identity that's worth working out yourself. And what allows us to then evaluate Q of F. Now, Q of F, the structure of Q of F is interesting. As an average of this exponential of some number times the fluctuating variable x, it is what's known as a generating function. What we mean by that is that it generates properties of the statistical distribution of x by taking a derivative, in this case with respect to beta f, the coefficient in front of the fluctuating variable x. More specifically, the log of Q of F is a so-called moment generating function. In that taking the derivative of Q with respect to beta F generates the moments of the distribution of X. For example, d log Q of F with respect to beta F will give you the average of X in that F ensemble. So that's an average in the presence of the force. Taking the second derivative, generates the second cumulant. Sorry, Q of F is a moment generating function. Log of Q is a cumulant generating function. The second cumulant is the variance of X in the F ensemble. We have an explicit expression for this here. All of the F dependence is there. We could evaluate that by taking that second derivative, and what we would have found is that the variance of X is alpha over beta, which is in fact the variance of X in the absence of the force. Additionally, the average of X in the F ensemble is alpha times F. Again, taking the explicit derivatives from that expression we have. Putting those two things together, we find that average of X in the F ensemble is equal to beta times the fluctuations of X in the reference ensemble times F. This is an example of things we saw you see in introductory courses, now made a little more microscopic. It's an example of a fluctuation dissipation relation, or a response relationship. The scale of fluctuations in the absence of the force tells you how, in this case, the average value of X responds to an applied force. In the specific case of the harmonic oscillator, this is exact precisely because that variance never changes with X. A simple graphical way to understand what we've just learned is to plot our harmonic oscillator. There's the example where F is equal to 0. I have some curvature 1 over alpha. If I added a constant force, I will shift the mean of that harmonic oscillator. But its curvature is left unchanged. The curvature, one can think about this just by completing the square, is left unchanged, but its new minima is at lower potential energy and positive x if F is constant. In this case, at location alpha times F. Indeed, one can solve for that minima explicitly outside of the partition function calculation by just taking the derivative of the total potential setting that equal to 0, and indeed finding that x must be alpha times F. So alpha tells you about the sensitivity of the minima to an applied force. But it also encodes the scale of fluctuations in the absence of a force. With an explicit expression for the partition function, we can go in and ask questions about the change in thermodynamic quantities. For example, the change in the potential in the presence of the force less that in its absence. Is going to be equal to minus 1/2 alpha times F squared. And that is identical to the change in the Helmholtz free energy. Given by just the ratio of the partition functions. If we go back up here, the ratio of the partition functions up to a factor of minus kBt, that will cancel the beta. So if I take that over that, take the log of that right-hand side, I have beta alpha F squared by 2 times minus kBt gives me minus 1/2 alpha F squared, implying that the change in the entropy is 0. So what we just learned, if we have a harmonic system, a system with Gaussian statistics, it will respond linearly to a linear force. It does so always. We did this exactly without approximation. There is a corresponding change in the potential, which is equal to the change in the free energy, because the change in entropy is 0. There's the same because the curvature is left unchanged, there's the same number of states before and after the applied force. That is true because the curvature is left unchanged, which you can imagine is unique to a harmonic oscillator. If we were to add a line to some other polynomial, the local curvature around its minimum might very well be changed. Nevertheless, this insight into how harmonic systems respond will give us some intuition for how we might approximate nonlinear systems, systems that are not exactly harmonic, by assuming that locally they have Gaussian statistics or they respond linearly. So those are the sorts of things that we'll explore as we actually start working on kind of really novel material, having kind of set the groundwork and reminded you of some basics of statistical mechanics in this lecture. So next up, in the upcoming lecture, we will talk about under what circumstances you should expect to find locally harmonic fluctuations, those locally Gaussian statistics, which turns out to be pretty ubiquitously true. This is due to something we will prove next lecture. The so-called central limit theorem tells us that universally, systems of finite correlation will have locally Gaussian statistics, and therefore we have just uncovered a means by which we can understand their response. All right, so look for that, and I'll look forward to seeing you in the live session where this week we'll break out into small groups to then start beginning live group or small group discussions in the upcoming week. All right.